Hi, I'm Khai from the Nest Lab at Worcester Polytechnic Institute, and I'm very excited to share our work on minimalistic collective perception with imperfect sensors. Our work attempts to answer the following research question. That is, how do we perceive the environment using robots that have impaired sensors? We address this by performing collective perception. So, what is collective perception? It's a technique that combines state estimation with consensus. So robots must both estimate and agree with each other. Collective perception can be applied to situations such as moon mining or wildfire fire detection, where you would need to estimate the distribution of a particular feature. In the moon mining example, for instance, you may use a swarm of robots to identify the distribution of the mineral that you want to mine. In our work, we study collective perception using the abstraction of a black and white tiled environment. The robots would perceive the feature to estimate the environment parameter. The estimated parameter target in this case is the fill ratio, that is, the average number of black tiles in the environment. In this field of collective perception, we have the seminal work of Valentini et al., where they proposed a voter and majority-based model approach to the best of two problem. Best of two problem is simply the case where you would decide if the environment has either a majority of black tiles or a majority of white tiles. So in their work, they assume that the swarm has perfect sensing. Similarly, Ibert and Abdelli's approaches to the collective perception problem also assume robots with perfect sensing, albeit they use a probabilistic based approach. On the other hand, Crosscomb et al. Proposed a voter model approach that considers a swarm with only a subset of flawed agents. Now, both Abdelli and Crosscomb's approaches allow them to solve a best of n problem this time, where the swarm would pick one out of n options of the environment fill ratio. Our work is distinct from those mentioned in the previous slide. Namely, we consider all robots to have severely impaired sensors. Our optimal and probabilistic framework is derived from first principles and has minimal requirements. In general, our approach has 3 steps. Each robot in the swarm would first compute an optimal local estimate with imperfect sensing, then communicate that local estimate with their neighbors, and then finally combine the estimates from the first step and the second step into an optimal informed estimate. Specifically, in the first step, the robot would use maximum likelihood estimation to obtain the local estimate, which is its best guess of the fill ratio based on its imperfect observations. Then in the second and third steps, it would use essentially what is the decentralized common filter to combine their own local estimates with their neighbor's estimate into a final informed estimate. With our approach, we showed that impaired robots can make accurate decisions in difficult environments consistently. One of the most significant results in this case is the case where the target fill ratio is 0.55. This means that the environment is ambiguous to the robots, such as this environment on the right. You can see that this tiled environment, about 50% of the tiles are black and another 50% is white. The result is shown here in this chart, where we plot the fraction of robots in the swarm making the correct decision across time. So the higher the markers, the better the decision-making performance of the swarm. Here, it can be observed that the swarms with some of the worst sensor accuracies can still make highly accurate decisions in picking the correct fill ratio. In addition to that, the entire swarm eventually came to the consensus on the correct decision. So with that, I have plenty of interesting results that I'd love to share with you. So please feel free to drop by my poster to learn more. Thank you.